really wasn't much except for it took a long time to grasp it all. Yeah. When you offered to take charge of it, I was like, I'm not gonna fail.
Okay. So let's see, it's been a while since the last lecture, but we got into this admittance and impedance analysis for a standard model of a piezoelectric transducer. And we discussed that a little bit. Here it is. It's really simple. You get this piezoelectric material, and the mechanical and electrical are coupled. When you put a voltage on there, it can squeeze or expand. So that's the mechanical. There's a mechanical motion there that's modeled by just a damp simple harmonic oscillator. And it has two, sorry, I severely bit my tongue over the weekend, and I'm still recovering from it. Sorry, that's why I'm having trouble talking. So you have two capacitor plates, right? You put the voltage on there, and that's modeled here. This leakage resistance is typically very large. You don't really, we'll usually won't deal with that. So we want to explore this circuit, and we're going to look at it from an admittance point of view. There's an advantage to that, as you will see. Remember, the admittance is just 1 over the impedance. Okay, so this is the input. We're going to look at the input electrical admittance. There'll be a purely electrical part that occurs when you mechanically block the system. And then due to the mechanical motion, there'll be this motional admittance. So the admittances, impedances in parallel add and reciprocal, right? So, if you have two impedances like this, the equivalent impedance here, when I say, I want to just make sure, I've said this a number of times before, but I want to make sure everyone understands this. This is what we mean by they add and reciprocal, right? So the reciprocal of this is equal to the sum of the reciprocals, all right? So that means that the admittances add when they're in parallel. So that's what we're doing here. We're adding the admittances. The electrical admittance, they're in parallel. Those two are in parallel, so they simply add. You just add these. But you got to remember, you're not adding the impedance. It's 1 over the impedance of these. So that's why we end up with, So 1 over the impedance here, 1 over the impedance there of those individual elements. The motional admittance, now we have a series. So the impedance of that series is the sum of the impedances, right? And then we have to take 1 over that to get the admittance. So here's the motional admittance right here. And we can represent that simply, multiply through by n squared, where n is, the ratio of the number of turns, but it's really, in general, a complex number. We multiply through by n squared, we get this. We can write it like that. And this is the standard damped harmonic oscillator impedance. We're going to consider the free mechanical case. And I don't know if I've pointed this out to you, but this is really important in sonar analysis because you've got something that's meant to operate underwater, and you can test it in air, and air, compared to water, air is like a vacuum. So in sonar transducers, we can easily access the free mechanical case just by running it in air. The air has just really negligible effect. Always, or almost always. So you'll be doing this in the lab. Well, that's one of the reasons we consider this free case here. So with no load, we zero out the load. And just substituting Z, we get this as the admittance. So here's the idea the overall idea here is that we want to determine parameters of the transducer or confirm them. So experimentally. So if you look at we look at the electrical, it's easier, as I've mentioned before, it's much easier to deal electrically with something than mechanically. So we look at the electrical admittance. And the natural thing to do here is look at this in the complex plane. So the real part of the admittance is the conductance. Remember, the imaginary part is the susceptance. So, I see I got a little ahead here. I thought this was going to be next. So we separate it into real and imaginary parts. It's very easy to do. Done this a number of times. We get this. Now, I don't know if Brian says this, but we're going to make an assumption here that the turn, we don't need the squareds, I'm going to get rid of those. We need to make an assumption that the turns ratio here, that's in general a complex quantity. We're going to assume that it's real, and that's often the case for sonar transducers. So we'll assume that that's real. And now we identify the real part, the susceptance, and the imaginary, the conductance, and the imaginary part, the susceptance here. Now, Brian keeps referring to admittance circles. A resonance has the signature of a circle, and transducer people use this word circle. And it really annoyed me because I couldn't prove that it was a circle in general. I tried. It gets pretty complicated, okay? So I finally just bailed out and did a plot. So this is my plot here of the real part of the admittance, the conductance, versus the imaginary part, the susceptance. And what I did here, because I was just after this, the pure mathematical statement here, is, are these really circles? Well, no, they're not circles, okay? This is not a circle, right? But what happens is, and this is, I don't really know why, but for typical sonar transducers, it ends up being really close to a circle very often. Very often it's close to a circle, right? It's not exactly a circle, as you can see from here. Now what I chose here was, I was after, I got tired of doing the analytical stuff, so I just wanted to see if it was a circle. So I chose all the parameters to be 1. I just took everything to be dimensionless and chose everything to be 1. This is not very realistic. I mean, this is typically infinity, okay, not 1. The blockage resistance or the leakage resistance, same thing. So this is not practical, but you can see here that you get this loop, okay? But as I said, typically for sonar material, it turns out to be pretty close to a circle. It's not exactly a circle, and we'll see that in some of the plots, some of Brian's plots. Now, another thing I got to tell you is, you only get this quasi-circle when you have the same units down here and here. Okay. Obviously, if you have a circle here and then you compress this scale, it's going to be an ellipse, right? Okay. I just want to point that out because this will come up in the lab. Okay. Okay, so that's why I did that. So, resonance here. We're going to talk a lot more about, today, we're going to talk a lot more about resonance. It's not real simple when it comes to transducers, as you'll see. But there is the typical mechanical resonance you know, the square root of the stiffness divided by the inertia, the usual mechanical thing. And that's, here you can see, setting these two equal, that gives you the mechanical, S is used for series mechanical resonance here. And remember, the compliance is the reciprocal of the stiffness. So this is just the square root of S over M, right? The usual mechanical thing that you know from 3119. So this is in the neighborhood of the resonance here. This is very low frequency. Comes up here, makes this impedance loop, this admittance loop, excuse me. And I don't know why, I haven't noticed this for a while. I don't know why. This is kind of weird. There must be a reason for that. This is where they intersect here. I didn't look into it. Oh, it's probably having to do with the fact that I've put all these quantities equal to 1. Probably not interesting. Okay. Now the textbook takes us a little further. Remember, we have a free. We're assuming this is free mechanically, that there's no load on the mechanical side. So if you do that, it's going to change this. Pretty obvious. And we'll go through this in more depth very shortly. In fact, right now. Okay, any questions about that? That's just sort of really an introduction to what we're going to do next. So I want you to look at this. We're going to get a lot of mileage out of this. This is the simplest model of piezoelectric transducer. Okay, it acts like a capacitor, but the distance between the plates can change, and we model that with just a mechanical damped harmonic oscillator. Now you'll notice that these are capital M here. These are electrical quantities. This is a fully electrical equivalent circuit, which is what we need to get into depth here. You know, we got away with it for a while when we were just dealing with the canonical transduction equations. But now we want to see graphs, we want to get into details. We have to make this, we have to do this precisely. So these represent the corresponding electrical quantities to the mechanical quantities. Now, Brian doesn't say, this gave me some trouble. Is there a load here, a mechanical load, or is there no mechanical load? Well, there's two ways you can look at it here. We're doing this, there's essentially no mechanical load, which typically doing it in air is a very good approximation. Or you've incorporated the load into these quantities. You can look at it that way too. Doesn't really matter. Now, so this is a little disturbing, you know. This is mainly a course in sonar transduction, right? And here we're sneaking this in without really showing the physics behind this. But don't worry, that's going to come later. We're going to actually derive this in one special case. We'll derive it pretty rigorously. It's what's called a ring vibrator. It's a piezoelectric ring that's plated and it expands like this. So you can drive sound or you can pick up sound. So we will actually derive this later on in the course. But right now it's a natural assumption to make. Just think of a parallel plate capacitor. Okay, so again, we're going to look at the admittance point of view. We've gotten rid of the leakage resistor. Typically, that's a good approximation. So, one of the things, this is not a big deal, but one of the things you want to realize here is that the admittance is simpler to look at here. It's easy to get the real and imaginary parts. If you were looking at the impedance, it would be It's more difficult to get the real and imaginary parts. Now that's not a real big deal, and it doesn't seem like much, but it's really sort of a tip of an iceberg here. And we've already started to see it, that it's just often more convenient to deal with admittance. Okay, so let me go from the text here. So I can't quite get this on. Yeah, okay. Oh, that's good. Okay, so again, this is the impedance plane, the real part called the resistance here, the imaginary part called the reactance, as we well know. And this is the admittance plane, conductance and susceptance. And now these are simply drawn to be exact circles. But it turns out, you'll see this in the lab, they are pretty close to exact circles, okay? And we will later, eventually today, we'll see somewhere, yeah. We'll see the breakdown from a perfect circle. These were simply drawn as by a graphics artist with a template. You guys have no idea, probably no idea what I'm talking about. They actually had these plastic templates where you would put, you had this pen and you would draw. Now we just do it all on a computer, but that's how I'm sure these were done, okay? So these are drawn. There is going to be a little breakdown here, and there has to be, because we asked the simple question here, what happens as a function of frequency? Well, the admittance here, and it's very easy to analyze this. I'm just going to state the results, but it's really easy to look at this at near zero frequency, okay? This is gone. This is gone. This goes to zero. So what's the admittance in the limit of zero frequency? It's just going to, no, it's actually, okay, I guess I misstated this. This becomes very large, so it dominates that. So then 1 over that, so it goes to 0. Okay, so, and similarly you can look at it at infinity. So here's what happens for the admittance circle. It starts here for 0 frequency, goes up here, goes around there, and then runs off to positive infinity at infinite frequency. Okay, so from that fact alone, this can't be a perfect circle, right? Just no way. The curve, the curve is a nice smooth curve, and it looks like, it looks like this. So this can't be a perfect circle. It absolutely cannot be, because this is a very smooth curve here. So wherever this starts, okay. So we'll see that evidenced in some graphs later. But anyway, it tends to be very close, which is nice. And the reason that's nice is we're going to see that. But let me point out what does this do? Well, you can show here that the impedance also goes, as you increase frequency, it's clockwise. And I made a little misstatement in the notes. I will correct that. So what it does is, it's not exactly the opposite. It starts at minus infinity for 0 frequency, comes up here, and goes like that. Okay, it's really what it has to do. So, okay. Now there's a lot of properties here. Let me look and make sure I'm saying everything here. Okay, so one advantage of admittance you can see immediately here. Look at the diameter of the circle. Here it immediately gives you a mechanical quantity, 1 over the motional resistance. Okay? But here, what does it give you? Well, you've got to worry about this quantity, this reactance quantity here. the reactance associated with the center of the circle, X naught. So that's an advantage right there to admittance, and there are other advantages, but you can see one straight away right there. Okay, so now what I'm going to do is, let's see, okay, good, that fits. Now in one of the labs, and it could be, I can't remember, it could be the one next week, you're going to go through and determine a number of specific frequencies here. So again, as you sweep frequency, you go around this circle. The resonance is represented by this circle here when you're in the region of the resonance. And there are a number of different particular, specific frequencies here. And so, it's not just like in mechanical oscillators. It's not just one resonance frequency. That's just one of these frequencies here. So I want to discuss with you right now these. Some of these have simple formulas. Brian has put them there. Some are more complicated. Okay? But it doesn't, when you're doing an experiment, when you're diagnosing this with experimentally, you can just pick off these points. For example, this F sub S right here. Maybe that's not a good example because that's the standard. Well, this is the standard mechanical frequency, as we were just talking about. The square root of the stiffness divided by the inertia. It's represented by this point right here. So as you sweep through frequencies, when you're at this point here, with the greatest conductance, the frequency corresponding to that point will be the standard series mechanical resonance. That's what the S is for. Okay, but there are all these other frequencies. So this is a little bewildering the first time you see it, or maybe the first two times you see it. But one thing I want to point out is often it's not a real big deal. They all, unless you have a real low Q system, which is not typically the case, all these frequencies are going to be in a neighborhood of each other, okay? But it is interesting here that we have this array of all these different points here. So let's go through these. I'm going to leave this up there. It's on the next page, but I'm going to leave this up so that we can refer to it. And then in the end, I will go beyond the book a little bit and tell you why the simple mechanical series resonance frequency is perhaps the most important one. All right. So, but for right now, let's go through all these. So the first one here we're going to talk about is the frequency of the maximum admittance and the minimum impedance. Now, by maximum and minimum here, these are complex quantities. So we mean the modulus or amplitude, okay? So if you look here, the admittance, this is the admittance plane. The greatest modulus you're going to have is this one right here. That arrow is going to have the greatest length, obviously, right? For in the loop, the resonance circle here. All right, and I don't know if I've ever generated Brian doesn't give us the formula. It's probably complicated, but I don't know. So that's one of them. Okay. He doesn't do these in the best order, but let's go on here. So that corresponds to this point right here. This arrow here is the greatest length when you go all around this circle. There's the one I was just talking about. This is, you recognize, remember, the compliance is 1 over the stiffness. So this is just the square root of the stiffness divided by the inertia. We call it the series mechanical resonance. That corresponds, it turns out, to this point right here. And we actually saw that in the previous, in that graph that I did with all the values equal to 1, right? So that corresponds to this point. Let me see, let me make sure I'm getting this right. Okay, I should follow the notes here. With every resonance, there's going to be an anti-resonance. The anti-resonance here is going to be the arrow with the shortest length. Right? Can you see where that is? That's going to correspond to the diametric, to this arrow right here. Right? Now, for the impedance, they'll be flipped. You know, this, because they're reciprocally related, the impedance and the admittance. Where you get the maximum here, it'll be the minimum for the impedance, okay? But that's this Fn here refers to this point right here. It's just that right there. Okay. So, yeah, I'm going to follow the notes here. Series mechanical resistance. Now, the vanishing of the input electrical reactance, that would be the KFS, KCF, KFCS definition of resonance, right? That corresponds to that point right there. Remember, it's the vanishing of the reactance. So that would be that point right there. Excuse me. I'm wrong. There are 2 points here, right? You can see where you have vanishing input reactance. So according to KFCS, you know, from a non-transducer point of view, a simpler point of view, that gets you a lot, right? It just doesn't work real well here, but we have 2 of these. They will correspond to resonance. This is the resonance, the one with the smaller magnitude of the impedance. This is the resonance that'll be anti-resonance. And similarly, there's an analogous or corresponding points on the admittance graph. And the reactance and the susceptance are not reciprocals of each other. Remember, it's more complicated than that. But when you're looking for zeros, it's going to be the same. So we give the same thing here, except they're flipped, right? Okay. Okay, moving right along here. Here's one that threw me for a few years. This F sub P. This is called the parallel resonance frequency. And it corresponds, it's related to the series resonance here. So here's the typical one, you know, the Oster one we're talking about. If you go back and look at this point, this arrow is not really carefully drawn. That refers to this point right here. The frequency for which you get that point is called the parallel resonance frequency, and you can see it's an anti-resonance it's an anti-resonance kind of thing. Okay, let's look and see what it looks like. Fs and Fp up here. Again, this is not very well drawn, but this Fs is this. And there's Fp. Okay, big impedance, at least bigger, a lot bigger than that. Okay. What does that correspond to? Well, if you look here, and I couldn't figure this out. What is this? You know what this is, right? Everyone know what this means?
Parallel capacitor.
Yeah. This is. Wait, excuse me. No, series capacitor. Capacitors in parallel add, right? We know that. And in fact, you know, the parallel plate capacitor, the capacitance is proportional to the area of the plates, right? So if you bring these 2 things together, it's obvious from the diagram here that the equivalent capacitance here is just going to be the sum. The capacitance is in series, add, and reciprocal, and that's what this is here. This is adding them in a reciprocal. So I couldn't figure out what was happening there, and then finally a student mentioned it to me. This was just a few years ago, a couple of years ago, I think. See, I guess we should look at this. Look at this circuit right here. These capacitors are in series, right? So there's an equivalent capacitance. You add them in reciprocal, right? So, when this resonates, when this circuit right here resonates, what do you see here? What if suppose you sweep this with frequency? What happens when you hit that resonance frequency of this circuit? Well, the answer is you're going to see a big impedance. How do I explain this? Let me look at the notes. I guess maybe the best way, and I mentioned it in here, is to think of a notch filter. Or, from an acoustic point of view, and this is actually done, so this is done in practice. You have a duct here. So when you send sound, a lot of ducts can emit really annoying noise. So at one or more frequencies. So what they do is, I don't know if we mentioned this before last quarter, they can hang a Helmholtz resonator here. At the and you tune this to be the frequency the frequency you want to remove. So when sound's coming down here, okay, and it matches the resonant frequency, you're going to get a resonance here. So this is the acoustical analog of what's called a notch filter in electrical circuits, where you want to remove a frequency. So as you sweep frequency here and you look at the amplitude that comes through, you're going to get look at the amplitude, you're going to get this notch there. So it's really obvious. I should have seen it, but it shouldn't have taken a few years for me to see this. But that's the physics behind this parallel frequency here that you see. It corresponds to that circuit, the circuit here resonating. So that's this one right here, FP. So I think at this point we've discussed all those. And like I said, you'll get a chance to actually do these, to hunt for these in the lab. Now, so this, I found this really confusing the first time I saw it. And I was just thinking, well, so what's the best resonant frequency? Well, you can make the argument, and Brian doesn't talk about this, but you can make the argument, we're dealing with a transducer, right? That you want to maximize the modulus of the transfer impedance. So if I'm thinking of this thing as a driver, I'm putting a voltage across here, that's my drive. What's important on the mechanical side is the velocity, or in electrical units, the motional current. So I think that's a very reasonable thing to say that. You can go the other way too. You can go the other way. I don't know if I mentioned that here. But you can go the other way too. So you can play around with this. This is what I did the first time through. And it turns out to be equivalent to the series resonance. So I think it's a nice, that gives it more credence or more importance to the simple series, the simple mechanical resonance. And I already said that. Okay. So, the next thing, any questions so far? The next thing here is to look at actual plots. So this was a graphics artist did this, okay, with the the template and the straight edge and these special pens that. I'm glad those days are over. Okay, and. Now what I want to do is actually basically get real plots here. So we're going to choose values. So here are values typical of roughly typical of sonar transducer, or piezoelectric material. Here, see the capacitance. So again, this is real. This is like a real capacitor, but it corresponds to a stiffness or a mechanical compliance, right? And same way with this, inductance and the resistance. So we're going to do it for 3 different motional resistances that differ successively by a factor of 2. The mechanical resonance frequency here by design is nice and simple. It's 10 kilohertz. Okay, and these quality factors here are going to decrease because we're increasing the resistance, and it's 20. This corresponds to a Q of 20. This is 10, and this is 5. Now, the textbook has graphs of the impedance and the admittance, and each of those from 2 perspectives: amplitude and phase, and real and imaginary parts. All right? So it's everything. So you can look in there if you're interested. And I remember immediately, I wasn't going to put all those in the notes. So the important ones, the ones that look the best, you get the information from, is the admittance, and it's the real and imaginary parts. So that's what we're going to be looking at. But I just want to make sure you understand that there's more in the textbook on this. So, what do we see here? Let me bring these graphs up here. Okay, so again, function of frequency. These are, it's obvious from the font here. These are actual, well, it's obvious to me. I don't know, this is the old electrical box, the font that they would use. This is actual data, okay? I think. Or it just could be an old plotting routine. Yeah, sorry. It's probably an old plotting routine. You see this this probably looks like an old font to you. Does it look strange to you? Yeah. So this was real standard, a few decades ago. So here's the conductance, the real part, the susceptance, the imaginary part of the admittance as a function of frequency. And the first thing we notice here is that this just looks pretty close to a normal kind of resonance peak, right, for just a mechanical oscillator, 3119. I do want to, there is a difference there. Does anybody see it? You remember if you just take a simple harmonic oscillator, a driven damped simple harmonic oscillator, and look at the amplitude of the response, it doesn't quite look like this. See what, does it look like that? This is amplitude, not power. No, yeah, they don't spread like that. So the typical case, when you look at this, you have this resonant frequency here. You have a curve that goes like that. When you look at different quality factors, it's like that, yeah. So there's a difference here. See, this is protruding up. It's actually, there's a broadening of the bandwidth here. Okay. I shouldn't say that. That's happening here too, but right, because we come down 1 over the square root of 2 and look at the bandwidth here. We come down, it's going to be. So I shouldn't have said what I just said. It's just there's more of a broadening. I guess I could say it that way. Okay, because of that. So it's not identical. That's for sure. And what does this look like? The phase, the phase of the. Well, it's got this. What we're accustomed to in the simple mechanical cases, it just comes along here like this and goes like that. You have a phase shift of 180 degrees. So this is clearly this is more different, than this. This differs from the amplitude case, but it's roughly similar. And I guess the big thing here is that whereas in the simple, just purely mechanical case, you get this phase change like that for simple harmonic oscillator. Here, the slopes don't asymptote to zero here. There's some finite slope here and some slope there. That turns out to be useful, as we will see in just a moment. And one thing I want to point out to you, and you'll encounter this, the KFCS definition of resonance, remember, will be that is where the susceptance vanishes, just like the reactance, right? And you can see that that's not bad for high Q systems, but look at the low Q. Look at the Q of 5 here. Where's the resonance frequency corresponding to KFCS? It's not there, right? It doesn't, the susceptance doesn't vanish, right? So there's a big problem there, right? Now, these slopes are, it's easy to come up with expressions for these asymptotic slopes here as you get sufficiently far from resonance, or you get close to zero here, there's a nice slope. And I want to point something out here, and this is actually part of the problem with this method, is what's the asymptotic slope there? It might look to you like it's pretty much the same, but does that look suspicious to you? Is this asymptoting to a constant slope? It hasn't gotten there yet. It's still curving, okay? So it asymptotes actually out here at less of a slope than this. And it's very easy to look at this analytically. And the results, you can just look at our equations for the admittance. It's very easy to see that in the limit of low and high frequency, the admittance becomes purely imaginary. There's no conductance, it's all susceptance. And in the low frequency case, the slope is bigger than the high frequency case. And the ratio of the slopes is simply the ratio of these capacitances. Remember, this is the blocked capacitance, the blocked electrical capacitance. And this is the emotional capacitance. It's the electrical quantity corresponding to the inverse stiffness or the mechanical compliance. So you can see why this is useful. How could this be useful? You have a transducer, you go in, you take this sweep, you measure these slopes, you have two pieces of information there. What can you do with those two pieces of information? You can find C0 and Cm, right? It's two equations and two linear equations and two unknowns. Okay, so you'll actually do that. Now I want to mention here, it's in the notes somewhere. So this seems like a nice method to use experimentally to find the blocked and motional capacitances. But there is a problem. There can be, and one of them is that there could be other resonances out here. And you may get in the vicinity of one of those resonances before this has properly asymptoted. So that can cause a little bit of a problem. Okay? And again, I think you'll see this in the lab. Okay. So that perspective was the real and imaginary parts of the admittance as a function of frequency. We can also deal with the frequency parametrically, right, as a parameter. And that's what's done in the complex, that's what's done here. This is the complex y-plane. And now I want to point out, because I don't think I pointed out in the notes here, these are real plots. And you can see, especially in the low Q case, you can see that that's not a circle, right? You can see this intersection point right there. And that right there tells you these are all not exactly circles, but it is remarkable that when the quality factor goes up, they become pretty good circles, right? If you look at this. This problem here becomes relatively less and less important at a higher Q, and you get a nice circle. Okay, so let me look at the notes here. So these are the three different motional resistances, okay, or quality factors. And you remember the diameter is equal to 1 over the motional resistance, right? So this is the high Q. This is the intermediate Q, this is the low Q. 20, 10, and 5, I think. So that's useful. From simply the diameter, we can get the quality, the mechanical quality factor. The motional resistance, and from that we can get the quality factor. Oh, I do say not the curves are not exact circles, right? Okay, so again, you can look at the textbook for a lot more, many more graphs, okay, from different perspectives, real and imaginary parts versus frequency, or just treating frequency as a parameter, looking in the complex plane of both the impedance and the admittance. So there's a lot of graphs in there. And one of the things you'll be struck by is that the impedance just is more complicated, okay? And I mentioned one example right here, if you're interested. But it's the, I don't think it took Sonar people long, and we'll talk a little bit about the history of Sonar when we get more deeply into it. I don't think it took them long to realize that admittance was the way to go. You know, you're looking for anything that'll simplify your life. These are complicated systems. And so this is why we use, it's simpler almost always to use the admittance. Okay, are there any questions? We've got a few minutes. Anybody have any general stuff? So you're going to come by and see me with your preliminary lab reports, right? Okay.
You said a due date for the lab?
Oh. No, but how about the time of the next experiment? That's sort of standard. I think that, let's see, I gotta look because, yeah. So, it's pretty simple in the beginning. We had a lab the second week, you did it last week. The next lab is the fourth week. So why don't we make it due Friday of the fourth week, okay?
Next week, Friday.
That would be the week from this Friday, right? So you come by, and try not to wait until Thursday afternoon to come by and see me. I mean, I guess one group can, I guess, but I don't want to see everybody Thursday afternoon, okay? All right. And then we're going to finish this long chapter, we're going to finish this up this week, right? So then there'll be the second quiz. And the first one is pretty simple. I don't know if you guys have looked at the quiz. It's not very bad. Quiz 2, okay? Incidentally, quiz 1, and I feel bad about this. I think it's the first time it's happened. 5 out of 8 of you did not get the equivalent electric circuit. Even though I think just about all of you tested it. You can go to special cases to test an equivalent circuit, which is all. I've seen experts in transduction do this. Does that carry some weight with you? People who are, live, eat, drink, sleep transducers. They're just, that's all they just love transduction. I've seen them do it. They do it quickly. You got it's like it's like the joke about the fastest draw and somebody drawing a gun, fastest draw in the. Never mind. Do you want to see it? And then you say, do you want to see it again? It's so fast, it's an old joke, right? They do it really quickly, but I've seen them do it, okay? Now somehow you guys just weren't careful. 5 more than half missed it. You checked it, and you just didn't do the check properly. It's a little tricky, the open and closed capacitor, you gotta think about it. But usually it takes just a couple of checks. Now it could be just by coincidence that you can have the wrong circuit and it checks in one case. But when you go to like a second case, it becomes highly improbable that it's going to work for 2 special cases. That's my experience anyway. I haven't mathematically proved that. But usually with a couple of checks, if you're wrong, you're going to find out. But you have to be careful. You have to think what a short is and what it corresponds to, right? A shorted capacitor right? Which is what kind of capacitance? When you short out, I'm going the wrong way. Infinite capacitance is like what? It's like a short. It's like it's just a short. Zero capacitance is like an open circuit. You've got to make sure you use the corresponding mechanical part. And it's the compliance. So an infinite capacitance is something that's infinitely compliant. That means the spring's not there at all. Okay, it's broke, you've cut it. And it's the opposite case is like a rigid rod. It's very stiff. It's like a rigid rod. So you need to be careful with that. So I edited the quiz for next year. Hopefully, maybe it'll help. You need to be careful about that. Okay. So anyway, we'll continue with this. Oh, and I guess we finished the chapter. Right. We finished the chapter tomorrow and a problem session on Thursday. Okay.